All right, I want to thank everyone for joining us this morning. My name is Andrew Sautarelli. I'm one of the support specialists for the mechanical simulation products. This morning, James Kubli is going to be talking to you a little bit about submodeling. But first, we want to start off with a few poll questions here. So we'll start the first one. And just how would you classify yourself? Are you a designer, an engineer? Are you a full-blown analyst? So take a couple seconds and answer these. Looks like most people are leaning towards being an engineer. We've got about 60% people voted. All right, we'll go ahead and close that out, and we'll share the results. So it looks like most of you classify yourselves as engineers. There's a few of you that are analyst or a designer there. Okay, hide that one, and we got one more left here. And which version of simulation mechanical are you using? So there's a lot of different versions. Maybe some of you are still using Algor. So take a second there and let us know what version. All right. And it looks like most of you are using 2015. Still a few of you on 2014. Certainly do want to let everyone know that 2015 is the latest version currently available, and that'll be available on your Autodesk account to download if you're not aware of that. Okay. So at this point, I think we'll let James start his presentation here. James, if you want to take over.
Thank you, Andrew. Good morning, everybody. My name is James Kubli. I'm a product support specialist here at Autodesk, and today I'm presenting on submodeling. Just before we get started into that, we have done several of these webinars already. This is the 9th one for mechanical. There is, as you can see from our previous webinars, we've done welding, basics on MES, what's new, tips and tricks of meshing, and our most recent one prior to this was pressure vessel analysis. We announce these webinars on the forums, LinkedIn, by direct email, Twitter, and Facebook. So please spread the word. All our presentations are visible on YouTube, or are put up on YouTube after we're done. The YouTube channel is Autodesk Sim 360. I'd also like to note that today's presentation is downloadable. The archives for the models and this presentation here are available at the address below at the bottom of the page. Sorry, here I seem to have been missing a page. I wanted to announce real quickly that the subscription center is no longer. You now need to go to accounts.autodesk.com to access everything for downloading your product, and assigning everything that you used to do at the subscription center is now available there. So, apologize, missing page there. On to our agenda. We're going to be looking at submodeling, what it is, how to do it, a little bit of the setup of the full model. We'll be mostly focusing on the setup of the submodel. There will be some tools presented, but there are also some tools that I will kind of gloss over. Will already be present in the model. It just we won't go over it in the essence of time saving here. So what we're going to be looking at here is a signal bridge with wind loading. I got a little quick picture there of a signal bridge. All it is right now is just basically the structure. We're neglecting everything else on it right now. But we're going to take information from that larger model, and translate it over to a smaller section of the model, which we will model with a little bit more detail to look more closely at what's going on right there for other more specific questions that we're interested in. Oh, there it is. Sorry, looks like I got on the wrong page. So what is submodeling? The simplest way to describe it is that we're taking the results from a larger, more simplified model and applying some of those load conditions to a smaller area, a more detailed area with more specific parts or features that we want to look at more closely. In our example, we're going to be looking at the base, one of the feet of the bridge, to see whether our welds will hold up at the connection and whether our base plate, our mounting plate that we are fixing to our concrete pillar, is actually strong enough to take the loads that we're looking at. And then next thing we're going to do is we're going to translate the results. We're going to be using the element displacements and rotations, predetermined splits in the geometry. You'll see this a little better once we start looking at the full model, and then when it's applied to the smaller model. So for our full model, it's the signal bridge. We're doing a linear static analysis. Basically, we're assuming small deformation. We're using a linear static stress because the analysis time is much quicker. We can get to our results and start making design iterations relatively quick before we go into more detailed analysis. Element type, this is beam elements only. It makes it really simple to set up, define, and run really quickly. Our basic loads and constraints with this model, we're assuming fixed constraints at the base, no translation, no rotation. We are using wind loading as our major force on the model, but we're not doing a CFD analysis on this. So we're just assuming an evenly distributed force of wind on the structure. And we're also going to be looking at gravity, the stresses due to of its own self-weight. The submodel, again, we're going to use linear static stress analysis, assuming small deformation, and again, the benefit is much quicker analysis time. But with this one, we're going to have mixed elements. We're going to be using solids for the base plate and the foundation. We're going to have plate elements to represent the beams, and we're going to be using rigid elements to help translate the point loads that we'll be getting in the full model to a more three-dimensional object. And again, our boundary conditions, our loads and conditions, will be displacement and rotations that we extract from the full model. We'll be creating remote loads with the rigid elements to apply these point loads to the more 3D object, and we'll still be applying gravity. Now there are some tools that I'll be using. We'll be using probes to easily visualize the results when we extract the information, and then a minor thing, but 3D visualization, we'll be playing with that for the beam elements. Remote loads and constraints, another really important tool, and Excel. Nothing too fancy with that, just to track our information and to use it to transcribe from the full model to the small model. But if you'd like more information on most of this stuff, you can find more on our knowledge network at knowledge.autodesk.com, or even use the in-product help by clicking the question box or question mark in the upper right-hand corner simulation. Now there are some additional tools that we have that we won't be using. This is mostly just for the essence of time. Some of it's a little repetitive, such as the bolt wizard. The base plate is bolted down, and then there is some contact define, and there's also some issues with mixed elements when you're translating forces from one element type to another element type. They don't all have the same degrees of freedom. unfortunately, we kind of gloss over that because of the fact that that in of itself can be a whole webinar. And part-to-part reaction forces. By default, we don't see reaction forces from one part to another part in the linear static stress, so you have to change some settings in order to see that. That was mentioned in a past webinar on welding, and if we have time or a question, we can go back and I can demonstrate that for you again. But still, like before, you can find this information here on our knowledge.autodesk.com, or in product help can definitely fill in for you. So that brings us to our example model now. This would be our full model. It is our signal bridge. It's all beam elements. Our loading, we have an evenly distributed wind loading, just a simple force applied to all the elements. Fixed constraints at the base. And let's see, let's run the analysis here real quickly. Just take a moment, demonstrate the advantages of linear static analysis. All right, we're done. Already got our results, our displacements. We can look at our stresses, just review our model overall, see if, in general, it meets our design requirements. At this point, we're going to assume that the overall model does meet our requirements, and we're going to take a look at, those weren't supposed to be there to begin with. So we're going to take a look at this little section right here. This is our area of concern. This is this front foot. I'm going to turn off visibility. There we go. There is. Here's the section we're looking at. But let's make things a little easier to view. And let's disable 3D visualization. Now we can see the model. There we go. Now, these are going to be our 3 points. These are our 3 cut points from the full model. We're going to want to grab displacement values from here so that we can translate this to our submodel. So I'm going to select those nodes, and I'm going to add a probe so that we can see the results there. Now, I've already got some of the results translated, but we're going to look at this node right here specifically. So we're going to get our displacement magnitude. We're going to then get our component loads. Just give me a moment as I run through these. And please speak up if I mistype here. All right, but we also want to, because these are beam elements, they have 6 degrees of freedom, we want to include rotation here. So again, 0.064593. We'll go to the components now. Now, here's something important to note. Our rotational values are in degrees. So right here, I've already set up the math to convert all of our rotation into radians, because when we input them into the model, it's going to be radians only. So now we've extracted everything. I've already got the values for these other 2 nodes. We've copied over all the displacements. We've got the magnitude, each component direction. and magnitude components for both translational and rotational force displacements. Now we go on. Now, so here is our submodel. We're looking at a 3D representation, or 3D elements. Well, sorry, that's incorrect. Beam elements are 3D. We've got shell elements or plate elements, more specifically to model the beams themselves. And I've got a solid plate here to represent our mounting plate. And this bottom part is a base plate. That's our concrete fixture that we're mounting to. We're not interested in the stress in it. We just want to use that for the surface-to-surface contact between that the mounting plate or the base plate here will experience when mounted to that concrete pillar.
So James,
yes, sir.
It looks like we got a question here from Adrian, who wants to know how you got from that full model to the simplified representation, and how you define that submodel kind of region in the beam element model.
This is a new CAD model here. I had to create a new CAD model with the representation of the beam elements as surface geometry and some solid geometry. The solid geometry is additional. This is just surface geometry. I simply extracted that from the definition of the parts in here. So, for example, I had already split off the section I was interested in to new parts to make it easier for me to isolate them and grab the nodes. But to get basically the design is I just went in here, used the dimensions here, went into Inventor, modeled the new geometry, and created a new analysis. Did that answer the question? Did I get everything involved in that?
It looks like you did.
Okay, great. All right, we'll continue on. So this is the additional, so there are two design criteria that we're looking at here, or that we will be looking at. One will be the weld stresses, or not weld stresses, but weld requirements in the connections here and our strength of our base plate. Whether we need more bolts to secure it down, or do we need a thicker plate, or thinner. Maybe we are strong enough and we can go with a smaller plate. So we now need to translate the reactions or the displacements from our large model. We go here, take a look at the results. You can see the general shape between the two are very similar. One important thing to note is my coordinate system. They're both identical. If they weren't, we would have to do some translating of one axis to another axis. So keep that in mind when you're creating the submodel, to try to keep everything oriented in the same direction. Makes it much, much easier. So we need to apply our loads from our displacements from the large model to the submodel here. The difference obviously between the large model is that we just had point loads, and in this one we have a edge here that we need to translate this to. So our best, what we're going to do is we're going to create a remote load. That edge is selected, it's down here. We now want to define the center of this remote load. So I already added work points in Inventor when I imported this model into simulation. So I already have the center of the pipe here. So I use that point and generate load elements. So as you can see, we've now got a web of line elements that connect to all the nodes on the edge to this center point. We're going to define these as rigid elements. Real quickly, just define the stiffness. We'll leave it at the default. Click OK. Rename the part here real quickly. So now we've got a point reference that we can translate the displacements from the full model to the submodel. So we're going to use prescribed displacements, translation. We'll copy the magnitude in. And then we'll copy each component into the component directions. Add a stiffness, a high stiffness to it. We want it to force the displacement. The node is still selected. I didn't click on anything, so I'm going to right-click again and go to Nodal Prescribed Displacement. We'll set this to rotation. And as I mentioned before, our rotation is in radians. So having set up the math beforehand makes this much easier. Again with the stiffness. And basically we would have done this at all 3 points that we cut the model at. But because it's a little repetitious, I already did the other 2. When using prescribed displacements, you want to make sure that you have a value of 1 here for displacement. Where we need to keep gravity still, so we'll add that in there. And we're doing a little good on time, so let me real quickly show you how to do the part-to-part reaction forces. The vertical mast right here, that's part 3. That represents the larger diameter beam element here, the vertical aspect in the y-axis. I set that, by default, it's set to nodes and elements. I set that to ignore. And so what it should do is then output our reaction forces there where it connects between where part 3 connects to every other part. Again, that's in solution, that's an analysis parameter, solution tab, settings. The parts that you're interested in, set it to ignore. Now, we don't want to set the other part to ignore, the connecting part, because then we'll get duplicate reaction forces and the results will be a little confusing at first. But if you think about it, it's just simply duplicating the reaction forces on both parts on the shared nodes. So again, we only do the 1 part. Now we should be able to run the analysis. Everything is defined. We'll run the simulation here. I'd like to point out that if I am going too fast, I apologize. Don't worry, we are recording this. You'll be able to see it on YouTube and be able to review it at your leisure. And again, both models, both the full model and the submodel, are uploaded to our box folder along with the presentation for you to review it, again, at your convenience. There we go. Take a look at our displacements. Everything looks pretty good. Von Mises, how are we looking here? Wonderful. Some stresses there. Nothing really to worry about. Everything looks good. Our plate is holding up very well. In fact, probably a little stronger than what it needs to be. Maybe we can go back, do another analysis. Well, I have to remodel this. This is a solid. But we can see the current design appears to hold up. And another thing to look at. Our stress is there. Okay, good. So our design criteria, at least with the plate here, we seem to meet it. We're not experiencing failure anywhere. That's really good. And the other design criteria, weld. We wanted to look at the weld strength between these diagonal cross members and the main mast. So we'll take a look at reaction forces. And basically, from here, so we can't actually, we're not actually modeling the welds, but what we can do is we can use these reaction forces to then properly size our fillet welding. So we know we don't have any material weld failures with the model, and now we have our reaction forces. We can do our weld sizing to properly size the welds. And with our submodeling here, we can do different analysis types. We can look at critical buckling if we wanted to. With the full model, the beam models, it just looks at the buckling of the line in this situation. But since we've converted it to a submodel, we can then look at the subsection to see if we get buckling within the walls here. So that's an advantage of switching over to the submodels. We can then look at the buckling in the walls, which the critical buckling analysis with the beam elements is not going to tell us about that. So we've covered, that is the basics of translating the results from a full model to our submodel.
James, Dan had a question here.
Sure, we're on to questions. What's up?
Perfect. So Dan wants to know, why are there reaction forces on node 3 but not on node 1 or 2?
That's because, that's a good question here. Oh, that's right. I only set this one part to ignore. We want there's our reaction force on that node. It's because I only set this one part to ignore. That's why we don't see the reaction forces there from the part-to-part reaction forces, because this is another part. But there is our reaction forces for that part and the reaction forces for that part. That's why we only see it on this and along the interface between the two. We're only seeing the reaction forces on this part. Because these are set not to show.
So we have another question here from Marco, who's looking, at the first design scenario with the beams. He's interested in how to set up, I believe, beam end releases.
Oh, sure. Let's selection lines. What's a nice long line? There's a nice long line. Do it right here at the connection. Here's something that's handy. Look at element axis 1. So go to the view, element axis 1. Oh, lovely. Nice graphic. That's helpful too. So we can see from the arrow right here that element axis 1 is in this direction here. So we hover over here. Come on, there we go. Nice graphic. It also points out the I and J nodes at the ends of the line. So we get I as is at the beginning, at the base of the arrow, and then the arrow points to the J node. Keep that in mind as we're going to add beam in release. There we go. I and J node. So that's important. The I node here is this end of the beam element. The J node is this end. And basically we check which degrees we want to release. So if we want to say this is a universal pin constraint or connection there, we just release R1, R2, and R3. We can't see it right now, but there we go. We turn on loads and constraints, and now we can see the circle here. It's on this end of the line element. Shows us that we have beam in releases applied there. I hope that answers your question.
It looks like you did, James. Great job there.
Great. Any other questions? I may have gone through, I know I probably went through things a little quickly. If you want me to repeat a step, just feel free to ask, or any other questions not necessarily related to submodeling.
So Williams,
I think Adrian has a question here. Is asking.
So William's wondering where he can view all these webinars.
You can go to, is it SimTV? Let's go back to the beginning here. Autodesk Sim 360 is our YouTube channel. You'll be able to find all our presentations there, along with CFD, composites, robot structural analysis. Marwan, you said Adrian's got a question?
Yeah, Adrian is asking, saying it would be nice to be able to have the detailed geometry into the same simulation with the simplified one, so the boundary conditions can be automatically applied to the detailed geometry in a new scenario. So basically combining the your original, and that's how I understand the question, combining the original all beam model with the more detailed shell and brick model. I think you could do that if you wanted.
We could, yeah. I mean, you can have them both in there and then just suppress and unsuppress parts if you wanted to.
Or you can have a combined model where instead of applying the loads that you calculated in the original model to the to those center points where you had the remote load, you can just from that point continue on with the, so to speak, stick model, the beam model.
Correct. We could have these both combined in the same model. The advantage, though, of submodeling like this is it allows us to go through our design iterations easier. For example, in the full model, if I had the foot here, the base here, modeled as the shell elements, I would have to go back into CAD and rechange the geometry there if I needed larger or smaller beams in particular in that area. So in the full model, the signal bridge, I can easily go into the element definition for each beam and change the beam entirely from an I-beam to a tube to a pipe to a solid to a square, whatever. I can also change the dimensions of that without having to remodel the whole thing. And so it allows me to run through design iterations much quicker. And then I can translate that from the reactions or the displacements and then look at a submodel and just run through a submodel through the design iterations of a submodel quicker. But correct, it is possible to have them all in one single model. We could analyze them all at the same time too. But that also takes the analysis time would lengthen for that individual model, but it depends on the complexity of the model. Everything's relative here. In this example, I just took on something quick enough to demonstrate it.
That's right, and that is, one particular example of submodeling where we have one model, the first one being done as beam elements, and the other ones using plate/brick and brick, plate and brick elements. Sometimes both models have to be actually brick elements. So, you do want to decouple them. This way you can, like James said, have more iterations in one. And then once you're done with that, go to the next one with the loads that are determined from the first one. So each one could be a whole lot more involved and complicated than we saw here. So you don't want to do it that way. So yes, in this model you could have combined them both, but that was just an example of how you would do that, because typically it would be more complicated and more cumbersome, which is in the first place why you're doing something like that, doing two separate ones.
Correct.
Looks like we've got another question here from Steve. I don't know if you have anything prepared, James, on sizing the welds, but Steve's interested in if you could step through that process.
No, unfortunately I don't. I was trying to find some good documentation online that I can point to for that, but I did not find anything in time. The best I can find was general rule of thumbs on fillet sizes based off of plate size. I apologize, but no, I do not have anything prepared, and I have tried searching for it and did not find anything relatively quickly. Is anybody else, Andrew, Marwan, if you have a resource that you're aware of right now? I did not.
I don't have anything offhand, James. Definitely, might be worthwhile taking a look if you guys out there have your, machine design textbook or anything like that. I'm sure there's some documentation there about how to size those welds.
Mm-hmm.
Yeah, I don't have anything offhand either.
Apologize about that. I really did want to be able to reference that, but I couldn't find anything to reference. Any further questions?
It does look like the stream of questions has kind of died down here, so we'll give it another minute or two. But if you do have any questions, please don't hesitate to use the sidebar there, and we'll be glad to answer that live. All right. Well, I want to thank everyone for attending today. James, I think you did an awesome job answering everyone's questions. If you do have any further questions, don't hesitate to go to the simulation mechanical forums on Autodesk.com, or for those of you on technical support, you can always go ahead and create a support case if you have some issues you're running into using this technique.